In this video, we're going to have a look at how you can interpret the drainage of a region as well as the fluvial systems that make up that drainage system. And so when we look at these river systems that are across the landscape, a map generally is a wonderful resource in order to see our actual river systems because we're looking from above, we're getting that aerial view. And that gives us a sense of our river systems across their entire drainage basin sometimes, and we can see where our starting upper course streams are, where they join together in confluences and flow down towards your more meandering middle course streams within the actual valley. And then obviously as the floodplains widen, we move into our lower course. And so you definitely won't see a river going all the way from its upper course to its lower course on one topographic map, because the scale is going to obviously not be able to represent that distance. But certainly we can see extensive examples of our river systems and parts of that actual river network. So let's start off with the basics, the actual structure of our drainage basin. So if we have a looking at the actual river network, we can see easily that our rivers, whether they are indicated as perennial or non-perennial in this case, obviously with the dotted line, they are indicated with that blue line, okay? And here we can see I'm outlining the actual tributaries. So these are the tributaries that are joining together, making up that river network, okay? They're flowing in a northerly direction. So if we have a look at how we actually see that, we look at the confluences being the joining points between the various tributaries, and you can see that those little V-shaped joining points where the two tributaries connect are all actually pointing to a fairly northern location. Okay, they're not going to all be perfectly true north, but they are going in a generally northern direction. And so we can say that these tributaries within this little network are flowing in a northerly flow. Then if we have a look at our key, the next part of our actual drainage basin that we can see in this case is the source. So this little river network has the source high up in the mountains, and you can say that the source is really where, in that upper course, where that river is starting, where the water would actually hit the top of the Ceres Peak and start to flow over the land and into the crevices and cracks and start to make those really small streams that are the upper course streams, okay, the fingertip streams. So that is the source region for this actual river network. Then we want, and it's an area of land, okay? Then we want to be able to identify the interfluves. Now the interfluves is the high-lying land separating two tributaries. So this is this mass of land that is going to separate and be higher up, separating the river valleys that are carved between the tributaries. So that is the interfluve of land that is found between those tributaries in the network. Okay, so that high-lying land separates it out. And so if we had to draw that in a cross-section, you would basically see the high-lying land either side, like a spur, okay, and then you've got your little river flowing in the bottom, creating the valley below. Okay. Then we have to be able to identify where is there low-lying land and high-lying land as well, because we know that our river systems are all really driven by the influence of gradient. And so where we have a higher altitude to a lower altitude, we have a slope, and the connecting slope can be at varying gradients, either steep or it can be gentle. But because we have that altitude change, water is going to flow from an area of higher altitude down towards an area of lower altitude. And the way in which we can interpret that on a map is obviously where you have your mountainous regions is where we can say that is our higher land sitting at a higher altitude. Mountains obviously can be indicated by all the contour lines, so we've got extensive contour lines sitting in this region. So we can say that the west of Ceres, or west of Ceres town is the high-lying land, okay, covered in those contours, reaching really high altitudes, 1,200 meters. Okay. Then next to it, on the eastern side of the actual mountain, we've got the Ceres town, and the town has located itself in the valley because obviously towns need to be formed on flatter land. They're influenced by the surrounding relief. But we can also see a change here in the contour lines. There isn't the extensive contour lines that we're seeing in the western side of the map. Okay, so we're seeing contour lines further apart, and that then shows that the land here is flatter. And that's not just a change in altitude, because obviously flat land can be at a high altitude. What we're really also looking at is that it's the lowland, because when we do find a contour line, we can then work out that that height of that land is sitting at a lower altitude. So there's a contour that's kind of been chopped off in this example, but if we follow further, we can actually find evidence of spot heights. And this one sitting at 454 is showing me that that is the height of the sea level of that land, 454 meters above sea level, whereas our peak went all the way up to 1,200. So the highland versus the lowland. Okay. Then we also want to be able to identify a watershed. Watershed identification is quite important in this section, and so we have to remind ourselves firstly that a watershed is highline land that is separating two drainage basins. Okay, so it's like a ridge of land, almost like a roof, where the water hits the apex, and some of it is going to flow on the one side, and then some is going to flow on the other side. Now, in order to identify where this apex is, we look for the high-lying land at the top of that mountain or ridge, okay? And it's quite easy to see where that high-lying land is making its dividing line, because it is always going to show the flow pattern being different between the different river systems. If you look for your fingertip streams, there they start here, and then there's more fingertip streams flowing down the slopes this side, okay? We can clearly see there's a separation between these fingertip streams, okay? They're like the fingertips going down towards the hand. But if we have a look at the area of land between the fingertips, okay? So this area here, where the source is, that is the high-lying land that becomes that apex, the top part of the roof. And when the water hits here on the source region, it's either going to flow down towards the south or to the southeast, okay, or easterly, or it's going to flow this way and go a little bit more northwesterly and into this basin. And that we can see that those beginning streams of each river network, okay, are divided by this high-lying land. So we can then indicate that the highest, we can connect all the highest parts of the land and say that this here, this land represents the high-lying land separating one basin from another. And remember that basins don't have to be entire large primary basins like the whole Orange River Basin. We can say this is high-lying land separating this little sub-basin or river network from this river network, okay, like in this example. So that is how you identify your watershed line that is dividing up the water and saying you're going to flow this way, whereas your water can flow that way. So those are the main structural elements within my river network that we can see in this example. Obviously, the water then flows from these little tributaries into a main branch, and then that will flow through the middle course and the lower course and out towards the sea. And we can't see that here. We need to consider, though, what kinds of questions can be linked to the structure of a basin and identifying those parts. So often what we can ask is stream ordering here, because there's various confluence points, and we know that every time the river changes in terms of a confluence, we are changing an order, a level order. So we can say if these are our stream order 1 streams, okay, a 1 and a 1, at the confluence, the stream that leaves will then have another order, and it will either be a higher order or it will be the highest order of the two. So you can go through the theory videos to revise that concept. But the important thing is to be able to use the map as the source. And so if those are level 1s going into that confluence, a level 2 will leave. And so you could count or be asked to count the stream ordering all the way through to a particular point. Maybe as the water enters the dam, what level is it sitting at? Is a possible question. Then we could also bring in the concept of nick points, because this water is flowing into an actual nick point, an example of a nick point. Okay. Remember that there's 2 main types of nick points that you can get. You get your, I'm going to go to this section here in terms of the presence of our dams, but your 2 main types of nick points are going to be either nick points that are going to increase erosion, okay, or they are going to increase deposition. And it's all got to do with influencing the actual balance or equilibrium between erosion and deposition. So if the feature, basically a nick point, is where there's a changing gradient on the actual river's course. So a river will flow, and if it hits an obstacle that changes the way that it flows or changes the gradient in the course, we say that that is a point at which it is almost like being nicked. Nicked like you're nicking your stocking and creating a ladder, you're creating an obstruction. And so what happens is that changes the flow, impacts the flow downstream of that feature. If your nick point is a waterfall, okay, or a rapid, this is where we have maybe an intrusive rock layer. You've got that igneous, harder, more resistant rock, or you've got a nick point waterfall that has formed because of that rejuvenating river, and it's now hit that harder rock layer through that rapid vertical erosion. Either way, that hard resistant rock is going to actually make the flow of the water over it react differently. Okay, so downstream, as the water hits that resistant rock, it obviously can't break it down more easily, and so you result in a vertical cliff or the fall of the water forming. And then because we now have increased that gradient, the water flows over that increased gradient more rapidly, and so we increase its erosive power. So downstream of a waterfall and rapids, we're picking up energy. We are then increasing erosive power. If water flows into a dam, the opposite is going to happen. So if we consider our dam to be like this, with the dam wall, okay, man-made, we know that the river is going to flow into the dam, add water to it, and then if it can flow over the dam wall or through gates, that's what will happen. The point is that we are actually slowing the water down. So as the water flows into the dam, it slows down, and that then often is going to increase, firstly, deposition within the actual feature, so that causes a little bit of a buildup of sedimentation, and that obviously can reduce the amount of water that the dam can take, because we're now making the low level of its base a little bit higher because it's filled with sand. We're also obviously increasing the amount of sediment collecting in that water, so that the water in the dam can actually be a bit more murky, increasing what is known as its turbidity. But downstream of the dam, there's less water flowing, and so if we have less water flowing, we have less energy, and so we are increasing the chances of deposition occurring. Okay, so we can bring in the impact that nick points have just by identifying an example of a nick point on our actual map. And here you have the Ceres Dam. We could ask, what is the influence that the Ceres Dam has on the actual flow of the river downstream? Okay, so those are our main features. Often in a test situation, they like to ask you which direction the river is flowing in, and I told you about the confluences and how you can work that out. But if you can't use your confluences, you need to go based on altitude change, going from highland to lowland. And the way we see that is we look for our contour lines, because our rivers are going to cross those contour lines perpendicular like this, and they're going to travel from, say, the higher land to that lower land. Okay, just mark it in our colors, and that then will obviously be the evidence to prove that it's going from a higher altitude to a lower altitude, going down that hill. So if we use that evidence here as an example, we can actually say, let's use this one as an example, that our rivers over here, this one, okay, is flowing down into that valley. We can see that, right? And the evidence that is that it is flowing in an eastwards direction, okay, going from the west towards the east, so going in this direction, is that it is flowing from an altitude of, if this is the 840 contour, we can then assume this one is 900 because it's a darker index contour, okay, and then we can indicate that this one is the 1000 contour. So it's going from an altitude of 1000 meters all the way down eastwards, okay, into the valley. And at this point, we can even assume, we don't need to necessarily find that last contour to find an average and a general idea of the height, but we can see that the trig beacon close to this is sitting at 492. So it's at least sitting in the 400 mark of meters. And so we can say that it's going from an altitude of 1000 meters eastwards down to an altitude of 400 meters. Okay, using that contour evidence as proof to justify. Often what students do is they like to use a spot height to help them to use altitude evidence, and this can be rather misleading. The problem with the spot height is that you can only use the spot height as altitude evidence if the spot or the indication of that dot is either right next to that river or like on the bank of the river. So this river, that confluence of the river, is sitting at 175 meters above sea level. Whereas this one here, you cannot use this as a height indication because this spot height says the land there is sitting at 201 meters above sea level. So that's a good 26 meters difference in terms of height, which is quite a lot. And the reason we cannot use it, even though you think it's close, is that actually, according to the scale of the map, that spot and this feature here are actually quite far apart if we times that distance in centimeters out by the scale of the map. So your spot height must be really close to the river, and then you can use it as evidence to prove the direction of flow. Okay, another thing that we can use is the actual dam wall, because we know that rivers flow into a dam, okay, they fill up that dam, and then we have basically built a wall along the excavation that we created on that river to store the water in, so the big hole. We made a dam wall to then block the flow so that the water then is stored behind that dam wall. So what we find is that the orientation of the wall will always show us the orientation of where the water wants to flow naturally, because that's where it's blocking it. It's like the door that closed the exit point, okay? And so that shows us that if this is a southeasterly orientation of the dam wall, the river is flowing in a southeasterly direction. So if we take this back to our example, you can see here, okay, obviously there's this here which could be based on the fact that there's a road there or whatever to try and actually build up the dam and trap the water. But where the water flows out is important. Always look for where's that dam wall and where is the little tributary flowing out of there. Because that is where that dam wall is controlling that water and only allowing it either through gates or whatever. And so there we can see that that orientation is southeast, and so this river is going to be flowing southeasterly out of that dam. Okay, so the presence of dams, we've spoken about the fact that they are nick points, and that influence the fact that they can increase the sedimentation, which is the buildup of sediment on the floor of the dam, obviously reducing its volume. The whole point of a dam is that we're trying to store water, not store sand. So if we increase the amount of sand at the base, we're then decreasing its actual capacity to hold water. So if this is my dam, and I go and fill the base up, well, let's fill it with water first. Okay. Then if we drop a whole bunch of sediment on the base, we then are reducing the size of our bowl. And so we're reducing the size of the actual dam and its capacity. So sedimentation is quite a problem because it's obviously reducing the functionality of that dam. Sedimentation also is because there's lots of sediment building up in an area, which means lots of sediment is in the water. So the more sediment particles in suspension in the actual water being held in suspension, the more we're going to find that the water is murky and brown, and that is something called turbidity, which I spoke about already. And that is the increase in our turbidity levels of the dam. And that obviously can then lead to, if we look at our catchment management, that can lead to an increased chance of eutrophication. So the fact that the water is so murky, no sunlight can get into the water, so the plants can't photosynthesize easily, and they start to decompose. And that then means that they're going to start to use, and once they die, in that decomposition, they use up oxygen. So they actually then reduce the oxygen levels in the water, which then has a negative impact on the actual ecosystem and the life in that water system. So that's the eutrophication process and how it links to turbidity levels. Now, always consider what the dam's being used for. Look at the land use surrounding it. So if you see there's lots of agriculture, we know that it's got an agricultural function as its main use. If you see lots of industry around it, then possibly they are storing that water and canaling it or furrowing the water out. And often we actually just have massive dams for domestic use. So we are storing water for our own reserves so that we can channel that water to reservoirs and then channel it into our cities and actually provide water for the city. And then you have to consider within this entire section, but also with dams, the water quality levels. What are all of these functions and activities, okay, doing in terms of their impact on the actual water in that area? So really consider how are people settling in the area using the land? Is their agriculture having an impact on the water in the river system and the dam? Is there a potential runoff of pesticides and fertilizers going into the water, increasing the nitrates and phosphates levels? Is there industrial waste and toxins and chemicals being washed into that river system? Think about mining influence. So all of those activities and how people are interacting with the river system can come up, and we can look at how we are managing our river system in the area. Another question that we can look at is the types of rivers, and we can easily see the type of river based on the symbol of perennial versus non-perennial. But we know that this can get a bit more detailed in this section because it's not as easy as saying flowing all year round or flowing only seasonally in parts of the year. We know that we mainly can see, well, we actually have 4 different flow regimes. We have rivers that flow all year round, which is our perennial rivers, and it's all got to do with where the actual water table level sits. So our groundwater that's found underground, okay, is going to sit, its surface level, that water table level is going to sit at different levels depending on how much water is received from the rain and goes infiltrating into the ground and filling that groundwater level up. So it can sit at a lower level if there's less rain, and it can sit at a higher level if there's more rain. And what makes our river really is where that actual groundwater is intersecting with where the land has been carved away into a valley, into a little river bed. And so when we have the water table level intersect with the riverbed, then that is the portion of water that is exposed to the surface, making the actual river flow, okay? But remember I said that there are changes depending on whether there's more or less water being received. If there's a wet water table level and it sits above the bed of the river, it could be higher up. That obviously is indicating where the level is during a rainy season. If the dry water table level is still intersecting the bed of the river, then the river is always going to flow. Whether it's a dry season, it just hasn't dropped, the groundwater level hasn't dropped low enough to not intersect that riverbed. So we're always having flow because of where the water table is intersecting with our river channel. And so these rivers are our perennial rivers that are always flowing, not because it's always raining, but potentially because the river has carved deep enough into the groundwater level to always expose that groundwater level above the surface. Our non-perennials, though, those are the opposite, okay? So they are now going to only get that intersecting line during the wet water table or the wet season. So the wet water table level is going to obviously then intersect and allow for that water to be exposed. During the dry during the dry season, the dry water table level drops so low because it hasn't received enough rain, and the bed of the river is not actually eroded deep enough to intersect with it anymore. And so that's why that river then doesn't flow or really drops all the way down, because that intersection is not happening anymore. So that's our non-perennials, okay, the majority of South Africa's rivers. Then we can see also on a map, often you will see the non-perennial symbol like this, but it will be surrounded by a brown sediment shading. And that indicates to us that there's this brown sediment buildup, a deposition buildup, like a dry riverbed, basically almost like it looks like will look like a dust road. Very hard to see because these rivers don't have depth, because they're not flowing all the time to keep cutting into the landscape. And so what happens is that because they only flow after a big episode of rain, so there's a big thunder shower and it fills that channel and flows downstream and then dries up again, the water table level is always going to be below the actual bed of that river. Okay, it never intersects, and so that river can't flow all the time or at any point, only if there is a big episode of rain on the surface. So there's no indirect flow input like we have in the examples above. An episodic river, that's the episodic. An exotic river may look perennial in terms of its symbol, and you would need to know the context more in terms of the area that it is flowing through, a very dry area, but with this perennial sign like the Orange River, and it's flowing all year round because it has that wet source, not because of the intersection with that water table. So it will look like this in cross section. The water table levels are below the bed, but in this case now we don't have no water, we have water in the channel all the time because the source is adding water to it all the time and keeping it flowing. So we can then integrate the types of rivers as well as how they flow, their flow regime, into a interpretation of a map. Another thing that is important to consider is how that water is flowing. Okay, is it going to hit the surface and soak into that ground and then not flow above, as evidenced by little channels of river tributaries above? Okay, or so the water is actually sucked into the ground and you can't see it, so it's filling up that groundwater. Or is there some kind of barrier stopping that water from infiltrating and soaking in? Something is slowing or speeding that movement up and blocking it from being sucked into the ground. And so it is forced to flow above the ground in the form of runoff. So in this case, we're looking at that theoretical concept in the section of infiltration, so whether the water is going to get sucked into the ground, or is it actually going to run off the surface? So without explaining all these details, but just how you really see it on a map, consider all the various factors that influence the rate of infiltration versus runoff, and look for evidence of that. So when we look at our natural rural regions versus our built-up urban regions, you're looking for that natural woodland shading, indicating trees, forests, okay, anything that's going to increase the infiltration, and that is because it's intercepting the flow, it's stopping the flow, it's becoming an obstacle, forcing that water to slow down and then slowly get sucked into the ground. Built-up areas don't do that. We know that's artificial. It's like having an impermeable surface, same thing as the impermeable rock or the non-porous soils, and so therefore you're going to increase the amount of water flowing in runoff. So you've got increased infiltration, increased runoff. Gradient is always a huge factor that kind of overrides other factors, and that is whether you have steep slopes, contour lines very close together, or gentle slopes, contour lines far apart. The more steep the slope, the faster the water will flow, increasing your runoff. The more gentle, okay, the slope, the more slowly the water can flow, and if it flows more slowly, it has time to get sucked into the ground, increasing infiltration. In terms of types of rock, you can't see that. You would have to look at the fact file, and they might tell you the area is covered in an igneous batholith layer, like maybe pole, and then you know that that is an igneous impermeable rock, and then you could then describe how that influences increased runoff because of the fact that the rock is impermeable. The type of rainfall in the region, again, look at your fact file for some clues. Maybe they talk about lots of relief rain, convective rain, or there's soft soaking rain in the region. It's a high rainfall region, a low rainfall region, okay? And that all influences how much is infiltrated versus how much is going to run off. So that's how we integrate that into the map work. So if we again have a look at some of these examples that I've just discussed, this is a great example of how to identify that watershed. So there you've got your fingertip streams, okay, or facing this the south, the beginning parts of those streams, all flowing to the northwest. These fingertip streams are all flowing down this way to the southeast. The high-lying land separating those, creating the apex of that watershed. So the top part where the water will then divide is then the high-lying region that's being connected here. And so you could even think about it as a water divide, because it is dividing the water from one side to the other. Okay. Now, in this particular source, we can also bring in drainage density. So the amount of tributaries across versus, how many are flowing across an area of land. So you could calculate the actual density using the formula, and possibly you would be given a drawing of one of the systems from the map in the actual test so that it's easier to then work out that area. This is something that's been in the past paper. But you could also just describe the drainage density, and we can do that by just looking at the actual area and saying, the watershed that is in this region divides two areas of river systems. And we can say that the northern river systems are sitting at a higher density. Okay, there's more tributaries flowing on the surface, higher runoff. So much more water flowing on that surface, many more tributaries over that area of land. So there's a higher density. So we describe that as having a fine texture versus less tributaries flowing in the southern slopes, okay, over a similar area of land, and so that then indicates a lower drainage density or a coarse texture. Okay, in this example we can also see some kind of collection of the types of rivers. So what we were looking at in the drawings over here, what we can see here is a great example of what a perennial river would look like. Okay, you can see that width of that channel from one bank to the other. It's really wide, showing a great volume. Okay, so it needs lots of water in order to have that volume, and so obviously it more than likely either receives water all year round from a wet source, or it's constantly receiving water throughout the year, allowing for that perennial flow. Okay, but surrounding this river is examples of lots and lots of non-perennial tributaries. So they are all leading into that main river and helping to add water to the main branch. So those are non-perennial tributaries leading water into the perennial main branch. Here is an example of a river that is flowing episodically because it has that brown sediment. I'm going to get rid of my highlighting so you can actually see the real shading on the map. And you can see that that non-perennial symbol is surrounded by that brown sediment shading, indicating that this river, the Yasalachta, is flowing not only in a northwesterly flow, because we look at the actual direction of the confluence, okay, but it is episodic, so it is only flowing after episodes of rain, and it will then dry up again. So that's that first example, linking to the one over here, and then number 2, there's your nice non-perennial, and then your episodic over here. Something to also consider in this picture, we can see a clear indication of braiding happening here because the channel is being split, okay, and there's going to be land in between in the middle with a build-up of sediment, and that obviously is then separating these channels out, making it braided. And we can consider, well, why? Why is an increase of deposition here happening? Why is there the braiding channel pattern being formed? We could possibly say it's because the water flow is being slowed down. There's a weir that's been built here, a little wall that's built through the channel, which slows the flow down. So this is how we can integrate many of the concepts all into one resource. Right, the next thing that we can see is once you can see your actual structure of your drainage basin, we can see the patterns that that structure of that river network actually makes. And we know that there's various shape of land and types of rock factors that are going to influence various patterns to form. So the water will always flow where it can flow most easily. And so wherever there are cracks and crevices, the water will then flow into those regions. Where there's softer rock, it will flow more easily. And so the landscape, the type of rock, and the shape of the land really influences the pattern that the network actually flows within. And those are our drainage basin patterns. The various ones that we get are shown in this example. We're going to look at the most obvious one. Not obvious, well, it is kind of obvious to see, but the most common is dendritic. That's the one that looks like tree-like. And do remember that with this section of identifying your different patterns, the various questions that can be linked to this, okay, are identify the pattern, describe the pattern, so it looks like tree-like, it has branches that are joining acutely in terms of the confluence points and the angle. And then the biggest thing that's quite important is account for. Give a reason why it has that shape. Well, for dendritic, I'm just going to do dendritic as an example. For dendritic, we know that it's got to do with the fact that the rock in the area is uniformly resistant to erosion. So it's eroding all at the same rate. We don't have some hard layers and some soft layers within that same region. It's all going to be of the same kind of resistance. So it can erode at the same rate, and it may also then have a gradual gradient, and that then results in this tree-like pattern forming. So I've identified it, I've described it, and I've given a reason why it forms, and that's what will be expected. So let's look at some of the other examples. You've got your radial. If you've got that central kind of heel-like feature, and then the spokes of the wheel of the tributaries flowing down around that. Okay, so there they go down the slopes. with the central hill in the middle. And then you have the rectangular. Rectangular and trellis, students often mix those two up, so look very carefully at those examples. I think it shows it quite nicely in these two examples from the different maps. And so what you find is with rectangular, it has a very angular, part of the name, pattern. So you've got these kind of sharp angles, all right? But what's important is that you need to know that the rock in the area is basically a big prominent rocky outcrop of the same kind of rock, and you'll find that then has created joints along that rock layer that the water can then flow through. So the joints and the cracks that have been exposed are then going to be the areas where the water flows, creating those valleys, and so that creates the angular pattern. So it just flows all along the same kind of rock, but it has angular joints that the water is flowing around. Okay. Then what happens with trellis and how it is different to rectangular is that trellis happens when you have more of an alternating layer of hard versus soft rock. So the region is made up of harder rock, and here I'm indicating the harder rock that is making up the ridge in the area. So there's the high-lying ridge land, and that is alternating on that surface level with softer rock, which has been eroded away, making the valley. So you've got valley alternating with ridges, hard rock, soft rock, hard rock, soft rock. Okay, and what then that leads to is a big, firstly also the water will flow as a big main river branch cutting through, certainly with lots of energy cutting over time through that landscape, and it'll hit that ridge line and it will start to cut through it vertically, creating a puert. So it separates the high-lying land and creates a gap through the actual rock. Okay, and obviously the surrounding landscape is more easily eroded away over time. And we have tributaries, so you've got this big main branch running through, perpendicular to the actual ridges, okay, running through it. And then parallel to the ridges, you have your tributaries coming in at right angles. So there's the right angles. So that's kind of that network of how it joins as a confluence in right angles. And the puerts are the result of this. So we get these gaps in our ridges. So you can have a look at how it's separated out. So if I raise here, we can see that the river has flowed through the area, and we've been able to build infrastructure because the altitude of the land has been lowered to the same level as the actual surrounding valley. So that's kind of the definition of a puert in any case. So you've got the same level of land because of that erosion cutting through the puert and lowering it down. Okay, so in this example, we have a puert separating that ridge, and it's all got to do with that main branch of that river cutting through the actual ridges that flow that are parallel to each other. Then you get a parallel pattern, and generally, I mean, this is nature, it's not going to be perfectly parallel, but the tributaries look like they're flowing in a very similar angle to each other. And basically why that will form is you've got this dendritic pattern, but the change in gradient occurs. So it's not uniform or gradual in its change. It's going to be kind of gentle and then all of a sudden become quite steep. And at the part where it becomes steep, that is where we actually basically create these straighter lines of flow for the actual river. And that's where those tributaries kind of become more parallel in their flow to each other because of the steeper landscape that they're flowing over. So that change in gradient from steeper to more gentle will stretch those tributaries up those steeper slopes in a more parallel fashion. And then lastly, you've got deranged, which is really no pattern at all. Okay, so the area is geologically young. It's basically is formed only in the last few million years, million being young in geology. And evidence of this is there's no particular pattern. So you can just see very random flow. You've got very big lakes in the area, collections of water, lots and lots of wetlands surrounding the region, the Martian flay that we see in South Africa. You're going to see evidence of lots of deposition features, so possibly oxbow lakes, and quite kind of extensive, wide rivers that flow. Okay, often on a map we can use the various sections of a river to showcase some of the features that are found. And so we can think about our upper course, middle course, and lower course features and easily see them on a map, either in shape or by labels and various symbols. So let's have a look at some of the common options. So you've got waterfalls that are indicated with this double line along the actual river. So that then indicates that the water is falling at this position over the landscape, and it's often labeled waterfall. Okay, so look for the words. There you can see another example here of the waterfall in this region. Okay, then you can see the river mouth, because the river is entering into a big body of water, and if that often that big body of water is the sea, then you're going to see that that is the river mouth entering the sea, and we often label it with the name of the river and mouth, okay, or mont. Then we can see examples of meanders. Now the difference between these two examples of meanders, here you can see, so meander is a looping river, okay, it's got these big loops flowing along in its course, all right, and here we have loops as well. But the main difference between this first one and the second one is actually how it's cut into the landscape. This example of a river flowing in a meandering pattern is actually flowing through a landscape that is extremely steep, okay, very steep slopes either side of the river, and that then shows us that it's actually created a gorge, a very deep, steep river valley. And the only way that that will happen is if the river becomes really rejuvenated and starts this energetic new cycle of erosion and cuts into this very steep landscape. So we're surrounded by steep slopes with these meanders that will be cut into those slopes, and almost it's as if you are biting down into a sandwich, you're cutting into the landscape. So the level at which the actual river valley is sitting, the altitude, is going to be vastly different to the top parts of the slope. Here we're sitting at like 800 meters, okay? Whereas if we go all the way down to the river valley, where that river is flowing, it goes all the way down to about 440 meters, okay? So there's a good 400 and something meters in drop between the top part of the mountain and the bottom. And the only way that that river could have made that big decrease in height is if it got really energetic and vertically eroded deep into the landscape, cutting down. And that is the incised meander. Then if we look at a normal meander across the landscape, this here you can see that the change in altitude between the actual river valley where the river is flowing and the top parts of the slopes is not actually that much. So here you could probably say the altitude of that river is, it's flowing here at about 140, but it's going to be fairly similar. It's only about 68 close to this point here. So there really isn't that huge change in altitude. So that's not an incised meander, but rather just a normal meander on that pathway. Okay. Then we'll look at the cross-section of the meander in the middle course section. You can see the ports, which we've already discussed. So there you have that gap that's been cut by that very energetic river through that resistant ridge layer, opening up the landscape. Here, like in the previous incised example, this is a gorge. You can see that the river is flowing, okay, through the area, and on either side there's a large number of contour lines really closely, tightly packed, and that then shows a very deep, steep river valley. So if I had to do a cross-section from A to B through the gorge, it would look like this, very steep, okay, and deep. My river is not flowing through that. It obviously has a lower down to the base, and so we've got this river at the bottom, but it cut through that landscape over the millions of years through lots of vertical erosion, and obviously then made it a very deep, steep river valley, which is a gorge. In this example, you've got very wide meanders, okay, because they loop with quite an extensive bend, as opposed to the loops that we can see here. And in this example, they're not that wide either. Okay, so these are very wide, and you can see that the neck of the meander is really narrow. And that's quite important in this example, because the more narrow the neck, the higher the chance of those oxbow lakes forming. So revise the process of how an oxbow lake forms, and then be able to identify these little oxbow lakes forming near the meanders. Okay. And then the last feature we can see here is also the river braiding, which we already discussed, but you can see that the channel has been split up here, okay, and because it's split, it's flowing around, well, it has split around the deposition sediment islands or segment islands. So all that deposition is building up, helping to split those channels to flow around those islands and make that braided appearance. So those are the braided channels, and those are the segment islands making up the river braided pattern. As I said previously, you're not going to be able to see or follow a river from its source all the way through to the mouth on a topographic map, because of that scale being so different. In terms of the 1 to 50,000 is showing us lots of detail but very little land. But if you are trying to go from the source all the way through to the mouth, you want to see lots and lots of land and possibly less detail. So that's just the difference between your small scale and large scale maps, to remind you. So if we do look at sections of the map, and we possibly look at certain tributary networks, not of an entire major river, but of some parts of the river, we can see that this is a great example of river tributaries in their upper course, okay, flowing in an upper course in a youthful stage. We say that they're in the youthful stage because they are in the beginning stages. They've got lots of energy because they're flowing with a lot of energy over a steep gradient. And I can see the steep gradient because I can see all of the contour lines closely packed together. So I know that water is flowing quite quickly over that landscape and eroding it vertically with a lot of energy, making a very deep, steep, narrow river valley. So here we get the formation of our V-shaped river valley, which is very common to or characteristic of the actual upper course. Okay, so the V-shaped river valley. We can also see evidence of the fingertip streams all over here. Those beginning streams, so that's a great piece of evidence to prove that we're in the upper course. They are the streams that are starting up close to the source. And we can also see that there's no floodplain. Okay, the floodplain cannot form because there's no deposition. There's no lateral erosion and deposition happening. It's all about the vertical erosion. We're cutting deep into the landscape and down. We are not cutting across. So there's no lateral erosion, no widening of my river valley. Okay, that comes later in the middle course. So we're going to exclusively look at that V shape formed from vertical erosion. And so if we have a look at what that looks like on the map, having a closer look at the actual river valley, the way you find your floodplain, well, you're not going to find one here, but you look for where does that contour start, okay, next to the actual river that's flowing. And here you can see there really is no space between the two, so no floodplain development. And so because those contours are so close to the actual river bank, it proves that that floodplain has not started to form. So that's really how you could define and characterize your upper course using evidence from a map. If we had to then define the middle course, sometimes the middle course and the lower course look very similar, and so the answer could be middle or lower depending on how much information the map is giving you. Let's have a look at this as being part of a middle course example, because the reason I say that is that the actual floodplain is fairly narrow still. So it's started to form, but it's still narrow. So if I look at my first contour line closest to the bank of the river, and I look at that one on the other side, it shows me that the distance between my actual river channel, okay, over here, and my river and my slope over there is actually starting to form, but it's still fairly narrow. And so that then shows me that narrow, young floodplain that is starting to form. It's starting to form because the river is starting to flow over a more gentle gradient, allowing it to actually eat into the landscape laterally and starting to widen that channel. So we're going from being V-shaped to being a little bit more U-shaped. Okay, we're no longer cutting down, we're now also cutting down, but also widening it horizontally to widen out that V. And so that would be why I would then classify this as middle. The next thing to prove that it is middle is we have a look at our river and we say, well, look, it's making a nice meander in terms of a feature of the middle course. So we've got those meander loops, okay? And if we have a look at the meander loops, often you get asked to draw cross-section through the actual meander loop. And depending on which side is the inner bend versus the outer bend, that will determine what kind of cross-section you have to actually draw in terms of the orientation of where those bends are. So in order to identify it, your outer bend is going to be on this side here, in this case, on the right-hand side. You can see that's the outer bend, okay? And the inner bend is this inside land region. Now that we can see where the bends are, through that cross-section, you can actually then determine the gradient of each side of your river valley. So if I have the inner bend on the left, the inner bend, we know, okay, is always associated, let's just make a little key here for ourselves, the inner bend is always going to be associated with lots of deposition and therefore the slip-off slope. And my outer bend is going to be associated with erosion and a river cliff. So if you learn that those are the key words that we're looking for, then you can make sure that you add them to your diagram. So if we're drawing a deposition slope, you want to draw a more gentle slope that's built up through deposition. And as you move over, because now we're moving from side A through the bend, okay, and we're actually looking just at this little river valley here, but through the bend to your deposition outer bend, and I mean your erosive outer bend, and that then needs to be undercut, okay, and it needs to have a steep slope. I'm actually drawing this at a different altitude. So you kind of want to make the land at the same height, okay, starting point of B, starting point of A, and then we make this more of a deposition slope, and then we exaggerate that outer bend so we can really show that there's undercutting happening in that river bend, in that outer bend, and that is forming the river cliff. So then the water will flow like this, okay, and then the labels that are necessary are all those that are part of my little key that I said. So we want to say that this is the inner bend, where there is deposition, and you can think about your theory as to why, and then forming the slip-off slope, but just integrating it with the actual map. And then on this side, we have our outer bend, okay, where there's lots of erosion, faster current, and we have our river cliff. So just exaggerate the shape so that it really clearly shows that you understand the difference between a more gentle deposition slope and a steeper and undercut river cliff. If we look at the difference here with the bend that's on the opposite end, you can see how the orientation is different, and this is where we really have to be aware of it, because this is the inner bend here. Okay, you can see that is the inner bit of the loop. The outer bit of the loop is sitting this side. So now C is on the left, which is the outer bend. Okay, so if we start to draw, we say C is the outer, D is going to be the inner. There's my height check. So if C is the outer, that's where I'm making my steep drop, my undercut, and then going gentle up to my inner bend deposition. And then all the same labels can apply. So why is it middle course? It's middle course because the river is meandering. We've got our contours further away from the bank, so a nice narrow floodplain starting to form. Okay, and we can draw some cross sections linked to those meanders. And then lastly, if we want to try and prove that this is the lower course, there's some great differences that are quite obvious here. The first one is the distance between the contours. There are none here. Okay, so the distance from the actual bank of the river to where a contour would start is really, really wide, and that obviously shows a very flat, wide open floodplain, very characteristic of the lower course. And so we know from our previous cross sections, little sketches, we've moved from upper course V-shaped to middle course more U-shaped, where we had more lateral erosion, okay, to our U, completely wide U shape, and that is obviously where we have flat, wide open floodplain. On these flat floodplains, okay, we often use it for human activity, so we like to use it to build our infrastructure on. So you can see lots of evidence of roads, okay, nice and easy to build on. Okay, we can make nice straight roads when the land is flat. We can have railways, okay. We're also going to see lots of settlement. So you're going to see built up areas across those floodplains, a lot utilizing that flat land, okay. And often we can see farming extensively along the floodplains using that nice wide area and the close source of water. In this example, again, we can see one of the features of deposition, which is river braiding, okay, splitting that channel up, having those segment islands in the middle there, all right. And then lastly, you can see the position of the river mouth. The only reason I know that it's the mouth and that this is the sea that it's entering is because it's labeled. So we've got the river that is exiting out at that point into that main big body of water.